Very good. Okay, good morning everyone. The recording has begun. I'm grateful that the temperature has subsided a bit in order to allow this lecture to be given in comfort. Sorry for the rest of you. And welcome to lecture 3 of the course on superconductivity. So let's begin with a little reminder of what's been done so far. I know all the recordings are available, but it still is worth giving a reminder. So far, we've done a bit of phenomenology of superfluidity, but in terms of our attempts to describe it, we've had two goes at it. We first noticed that it looks a bit like a condensation phenomenon. So we started with Bose-Einstein condensation, which is a phenomenon exhibited by completely non-mutually interacting bosonic particles. Our conclusion about the Bose-Einstein condensation is it is condensed, which is good. It has certain two-fluid aspects, which looks good. But we ended up arguing that it is not superfluid because of this Landau argument. The dispersion relation of excitations in the Bose-Einstein condensate is still quadratic, which means that viewed from a moving frame, there are always negative energy things. When you try to flow it coherently through a pipe, the pipe wall excites those excitations and will destroy the superfluidity. So we conjectured then that the stabilization of superfluidity must be to do with interactions between the particles, if the non-interacting problem doesn't show it. And so we wrote down last time a theory for a weakly interacting Bose gas, WIBG in the trade, with just contact repulsive interactions between the particles. And we asked, what does the ground state of that system look like? And we spent some time discussing the fact that a good trial ground state would be this kind of coherent state, which is characterized by a complex eigenvalue, which has an amplitude and a phase. And we spent some time talking about the fact that in the coherent state picture, when you have a decent number of particles, states with different global phase are genuinely distinct. So just to emphasize that again, in single particle quantum mechanics, what you mean by phase is just the complex number standing in front of the wave function. That is not an observable thing, and states where that number is different are literally the same state. Here we're talking about coherent states, where the complex phase is part of the eigenvalue of the annihilation operator. That complex phase has meaning, and the states with different such complex phases are orthogonal to each other, or very nearly so. So what we did last time was to show that the ground state does indeed develop a non-zero eigenvalue of this coherent state. So let me just state in 2 lines what we did see last time. So we wrote a Hamiltonian, which was the integral over space of a kinetic part minus h bar squared over 2m del squared. And then we specialized to a contact interaction, which just involved looking at the density point R and having it interact with itself, basically. And we showed, under a coherent state, ansatz for the ground state, which just means that the annihilation operator acting on the coherent state is a number times the coherent state. We showed that the ground state is given by a uniform but non-zero value of this complex order parameter, and we worked out that energetically it would prefer to have the value mu over g. So we had to put a chemical potential in order to get any particles at all. But having fixed the chemical potential to get a certain number of particles, we discover that it likes to develop this complex order parameter with this non-zero magnitude. And so, of course, the point is that this doesn't fix the phase. And this is a modulus times some phase. And at this point, there is no energetic reason to pick one of these over the other. So this is a genuine symmetry breaking transition then. It breaks the symmetry between the complex phases of all those different coherent states, and it just picks one.
Okay, so that you did. Well, I have an even worse question in sense of my embarrassment. I think that I had exaggerated in my mind the power of the variational principle, and you made statements that, okay, we're gonna do a variational principle analysis, but you were pretty clear that that was only of value. If our starting guess had been completely wrong, it wouldn't have helped at all. So I'm just, I keep on telling my students never to be ashamed to ask one of these dirty questions that you really feel you should have understood. I clearly don't understand this possibly. I thought the variational principle would do more for you than that. So could you say a few words about it, maybe for my benefit and the benefit of some of the experimental students?
Sure. So, this is a variational guess at the ground state. And what that's based on is the variational principle, which says that for any state psi of a quantum system, the expectation value of the Hamiltonian in that state must be greater than or equal to the expectation value of the Hamiltonian in the true ground state, which we don't know. Mm-hmm. So that's the only statement that we can make with confidence. If we pick a certain class of quantum states and we work out the expectation value of the Hamiltonian in those states and say those states have some parameters, like our coherent state eigenvalues here, we can adjust those parameters to make this left-hand side as low as possible. Then we know that however low we get it, we will still be greater than the true ground state energy.
And if you made two guesses and you were able to adjust one of them to come to a lower value variationally than the other, then that's a better approximation to the ground state for sure?
No, not for sure at all.
Okay.
And that's the point, right? So the variational principle is only about total energy. The statement that as your total energy gets closer to the true ground state, other properties of the state get closer to the true ground state is a complete article of faith, and there are well-known counterexamples. People thought for a long time that there was no such thing as long-range antiferromagnetic order because they had such good variational states that didn't have long-range antiferromagnetic order. They thought, well, surely nature wouldn't be so cruel. It turns out nature is very cruel in the case of 3D antiferromagnets and very often gives you quite energetically competitive states that just don't look like the true ground state at all.
So in the spirit of disrupting this course completely then, if you make an ansatz state, is there anything that you could do to really examine the quality of your ansatz making? I suppose you're going to do it, you predict properties using the state and see if they...
Well, that's exactly right. I mean, you check against numerics or you check against experiment. And ultimately, the justification for writing this kind of ansatz is that the theory based on it is a very good fit to the phenomenological properties of superfluidity. And I think in the end, any such variational method is uncontrolled. It's not that there's some parameter where if you keep changing it, it will smoothly turn into the exact answer. So yeah, it's an educated guess, and ultimately I think the justification is empirical either in the sense that you compare with actual experiment or that you compare with, some quantum Monte Carlo, if you can do it, some unbiased numerics on the model that you were trying to describe.
And this is what happened with Laughlin's ansatz for the fractional quantum Hall wave function.
Yeah, exactly.
So it explained the phenomena, therefore it was thought to be right.
Well, different people would say different things. They also did a lot of numerics on small samples. So I think some people were more convinced by the match to the phenomena. Some people were more convinced by the fact that the ansatz wave function had a pretty good overlap with the best numerical estimates of the ground state.
Thank you.
Yeah, no problem. So yeah, don't take this for more than it's worth. We've made a good guess, and because the guess turned out to be good, this is the one I'm telling you about.
So the chemical potential here seems to behave a bit differently than in the Bose-Einstein condensate, where it was negative at high temperatures and it went to 0. But in this case, chemical potential is positive below critical temperature.
Yeah, that's correct. So that is a feature of having turned on the interactions. The non-interacting system would be unstable with a positive chemical potential, but the interacting system won't be, because at some point the repulsion between the particles will stop me from putting more in. So for the non-interacting system, if I can lower the energy by putting one particle in, then 1,000 will just be 1,000 times as good. So because it's a linear problem, a positive chemical potential means a complete instability. The interacting problem is non-linear, so just because it's good for me to put one particle in doesn't mean it's good for me to put two, and that keeps everything under control. So yeah, a positive chemical potential is fine. And you can sort of see what it's saying. It's saying that if I add a particle, the total energy of the system will go up by G times the condensate density, which is basically just a measure of the repulsive energy between the new particle and the ones that were already there. So it's quite an intuitive value for mu to take. Luke?
Yeah, I was just going to say about what you said. It doesn't feel like entirely a guess about a bit like what we were saying before. If we think about the partition function, and assuming there is some kind of minimum, maybe some small fluctuations, then it would be kind of a representative state, wouldn't it?
Yeah, that's right. Assume,
yeah. Worry about it just matching the energy, or then it would be.
Yeah, but what we never know is whether we found the only saddle point, right? So typically identifying saddle points of path integrals for partition functions itself depends on some sort of parameterization, and you never quite know if you've done everything. So what you would do to get this in a path integral language is make a Hubbard-Stratonovich transformation in the superconducting channel, look for a saddle point that had, or a superfluid channel, look for a saddle point that had a non-zero order parameter. You would find one and it would have these properties. But by itself, that doesn't tell you that there wasn't some other channel where you could have done it, where you'd have got a lower energy. And that's a much harder question, and is where things like functional renormalization group come in, right, to try and actually describe the competition between these different possibilities as the temperature is lowered. Here we're just saying, this theory can only give us two possibilities, superfluid or normal state. If the system decided to do a third thing, we wouldn't see it.
And could you say a bit more about the symmetry breaking, because that is one of the most fundamentally misunderstood things in superfluids and superconductors.
So one thing to emphasize is that it's importantly different in superfluids and superconductors. So don't go away thinking that everything we've said about superfluids here is going to apply to superconductors. I'm just warming you up with the argument in superfluids, but I'm going to end up telling you that in superconductors it's very different. And the reason it's very different in superconductors is because you're coupled to the electromagnetic field. That actually drastically changes the nature of the theory. So, people describe superconductors as charged superfluids, and to some extent that's fair, but that doesn't mean that everything you know about superfluids is also true of superconductors, and as we will discuss, there are important counterexamples to that. And what the nature of the transition is an important such case. So this transition is a genuine symmetry breaking transition. You can think of it like a ferromagnet, right? You have different patches of your sample which are approximately described as coherent states with kind of random phases, so random complex phases of the coherent state eigenvalues. but there is an energetic preference for those phases to lock because the Hamiltonian does not like anything about the complex order parameter to vary in space, be it the phase or the amplitude. So any spatial variation is bad from an energetic point of view, which means that firstly, different bits of the sample genuinely prefer to have the same magnitude of the superfluid order parameter, but they also, by the same token, prefer to have the same phase.
Because it's this phase that has this totally different meaning to the standard phase. You know?
Exactly. So this phase really means something. It's the complex phase of think of it like the phase of a wave. Right? You can imagine the different bits of the superfluid as different oscillators, and this is just like phase locking between those oscillators. And this shows that it's energetically favorable to do that. Yeah. So the transition is genuinely a breaking of that U1 phase symmetry. There's no problem with that in this context because it is a genuine symmetry of the problem. Condensate states with different total phase, in this sense of the term phase, are genuinely distinct from each other, and the system has just picked them. That's not how it works for superconductors, but we'll come back to that. Good. So, more questions before we dive further. Good. So, the question that we haven't addressed yet is, have we solved our problem? So we've written down an interacting bosonic system, we've got an ansatz for the ground state, we've determined that it develops this complex order parameter. I've been referring to that as the superfluid order parameter, but we have not actually checked whether this system is superfluid. So what we should do is run it through the Landau argument and see if superfluidity is stable now that we've added the repulsion between the particles. And remember, the thing we needed for the Landau argument was the dispersion relation of the non-condensed part of the system. So what we now have to do is to work out what the dispersion relation of the non-condensed part of the system is, run it through the Landau argument, and in order to avoid putting you in a terrible state of suspense, I will tell you now that we are going to discover that superfluidity is stable because the dispersion relation for low energy thermal excitations in the superfluid is linear, not quadratic. This was shown by Bogolyubov and is kind of the most important point. Now,
When you say in the superfluid, you mean in the state defined by the wave function that you've written down?
Yeah, sorry. Yes, I shouldn't assume my own answer. So yeah, in the state where this complex field takes a constant space in position independent value, we will now look at the energies of fluctuations around that and show that they are linear in the momentum. And that will give us the ingredient to put into the Landau argument and argue that there is a finite critical velocity. Okay, so I'm not going to do the calculation. I promised at the beginning we weren't going to do lots of calculations. I'm just going to give you a few bullet points about how the calculation is done and then tell you the answer. There's a bit more in the notes, as there usually is. So, but is this state superfluid? We as yet have no evidence that it is. So to check, we need E of K, the dispersion relation of excitations out of condensate. And so the way to do that is to go back to our Hamiltonian, but to expand around the state that we've now decided is our approximation to the ground state. So the idea is, let's take an operator for this annihilation operator for particles at position R, and we know that in the ground state, this thing is just replaced by the order parameter. So let's say that for an excitation, it is that order parameter plus some little correction. And so the idea here is that somehow the ground state is classical because it's just this number, but the fluctuations around it are still quantum mechanical, and so they're still represented by operators. And since the system is translationally invariant, it would make sense, rather than talking about the perturbation to the quantum field at a particular point, to talk about plane wave excitations. So I will do the usual thing and just do a Fourier expansion of these fluctuations in plane wave modes. So this AK annihilates a fluctuation above the ground state, rather than a particle. So the vacuum for these things is the condensate, not the true vacuum. And so we want to know what particles against this sort of condensate vacuum do. And if I substitute this into here and this into there, and I drop terms of order fluctuation cubed and higher, right? Obviously if I kept all of the powers of delta psi, this problem would be as difficult as the original, but what I'm going to do is to proceed on the assumption that the fluctuations are small, which means that higher powers of them can be dropped. And this allows me to get a linear theory for the fluctuations, even though I had to use a nonlinear theory for the ground state. So putting all of that in, one finds that the Hamiltonian can be approximated as some constant, which is just the energy of the condensate without any excitations, which one can work out by putting the relevant bits in. It's the condensation energy of the superfluid, but since we're mainly interested in the excitations, I'll just write it as E0. And then we find that there is a piece mu. So there's a piece that comes from the kinetic term, right? You can see there'll clearly be a bit where I put delta psi in on both sides of that, and that's going to get me something that looks like this. And then there's a piece that's the important piece in a way that comes from the interaction term, which is N0. I've just called this square modulus of the order parameter N0 times G over 2. And then we get an interesting structure. So we get A dagger K, A dagger minus K, plus 4 AK dagger AK, plus A minus K, AK. And to up to quadratic accuracy, that's what we get. You can see where these terms come from, because when I expand the brackets in this product of 4, I'm going to get 6 possibilities, right? I'm going to, middle row of Pascal's triangle, I'm going to get some where I take the classical bit from the 2 creation operators and the quantum bit from the 2 annihilation operators, and that gives me this term. I'll get a term where I take the classical bit from the 2 annihilation operators and the quantum bit from the 2 creation operators, that gives me this term. And then I'll get 4 terms where I take a classical bit from one of the creation operators, a classical bit from one of the annihilation operators, and then these from the others. So that's not difficult to derive, but the question is, what does it tell us? And what it tells us is that the theory for the excitations doesn't conserve the number of particles. So as well as this term, which just tells me that it costs energy to have a fluctuation in plane wave mode K, I've got these terms which spontaneously create a pair of excitations, if there isn't one, well, whether or not there's one there already because these are bosons, or spontaneously destroy a pair of excitations. Should this worry us, given that we started with a system where we were expecting the number of particles to be conserved? No, it shouldn't worry us, because this is the description only of the non-condensed part. What this is telling us is that it is possible for particles to emerge from the condensate in a momentum-conserving way, or to go back into the condensate in a momentum-conserving way. And which is why the rate of these processes is proportional to the density of the condensate. Notice that the statistics do not require this creation and annihilation in pairs. There's nothing wrong with annihilating a single boson. It's momentum conservation that requires creation and annihilation in pairs. If I'm going to take something out of the condensate, which is at momentum 0, and I'm going to make some thermal excitations which are at non-zero momentum, the only way to conserve momentum is to make them in pairs. So the picture you should have of what this Hamiltonian means is that it describes the dynamics of this kind of bubbling soup of thermal excitations above the condensate. Now, the interesting feature is that some of them are present even at 0 temperature, right, which tells us that our variational estimate of the ground state is actually improved by the inclusion of some of these fluctuations. It's, but that's not a statement. We will always get a better picture of the ground state by including fluctuation effects. So, do people think they have a sense of what this Hamiltonian is describing? This would be a good moment to ask if not, because now I'm going to tell you. Yeah.
Can you? So here, do we consider like a perturbation where we have something different, and we say that this thing different is we put it in the Hamiltonian instead of in the state that we change, or is it something else? Like, I don't understand why we change the Hamiltonian. I have the impression...
We have not changed the Hamiltonian. We've evaluated the Hamiltonian, which is given up. So this Hamiltonian at the top is the exact one that we want to deal with all the time. But it is a complicated quantum operator acting in a huge Hilbert space. And, if we could write down the exact ground state of this, we would, but we can't. And so our approach to dealing with it is to proceed in stages. We first look for the single coherent state, which gives us the best approximation to the ground state of this Hamiltonian. But then we try to improve that state by adding fluctuations around the coherent state. And so the coherent state comes when we say that I'm only going to look for solutions for eigenstates of this, not eigenstates, for approximate eigenstates of this Hamiltonian that are these quantum coherent states. And I'm just going to build it as a product of coherent states over the different modes. That's very restrictive, right? Because it means there's no entanglement between one mode and another. I'm really just looking for a sort of product state, and I just give a coherent state in each momentum mode, or equivalently a coherent state at each position, and then I just let the energy tell me how they ought to be related to each other. So that gives me the phase locking, but it doesn't give me any entanglement. The real quantum system is surely going to have some entanglement. So how do we bring that back in? We say, well, let's use our non-entangled condensate state as a starting point for an expansion. So let's now look at forms of this annihilation operator that are not exactly the condensate state, but are close to it. So you might think, well, why didn't I change the wave function up there rather than changing the operators?
Yeah.
But that's a choice you can always make in quantum mechanics, right? So you can think of the state as evolving with time and the operators are staying fixed, or completely equivalently, the operators evolving in time and the state is staying fixed. So I've chosen to let the operators evolve in time because it's just easier to do the calculation that way. But you could do either. So that's not a deep difference. Because in the end, observables are always made of operators sandwiched between states. So which of those you say is time evolving is entirely up to you.
Well, from the variational perspective, right, you can just restore the gradient term in your, it looks like a field theory basically, and then you can just work with that kind of, right?
Yeah.
You're looking at spatial variations of the order parameter.
That's not quite true, actually. Because if I were looking only at spatial variations of the order parameter, then I would have no non-trivial commutation relations. The order parameter is already classical. So actually that's going to be an important distinction. In a way, that's what makes the distinction between the thermal excitations and the zero temperature stuff that you do by applying boundaries and things.
Okay. It's like doing classical spin waves versus quantum spin waves.
Exactly.
You'll get the same dispersion,
Yeah.
but you won't get the correction to the energy.
Exactly. Yeah.
And for the heart of thinking, the classical state is classical because it contains a macroscopic number of particles.
Exactly. So the point is that we have for the original annihilation operators some commutation relation that looks like this, and all of the quantum mechanics is coming from the fact that that right-hand side is non-zero. But if one of these develops an expectation value that's of order n, then the left-hand side is of order n, the right-hand side is of order 1, and you can safely drop it. So basically, as soon as any mode becomes macroscopically populated, that mode starts behaving classically. Just because all the quantum mechanics is coming from here, and that becomes negligible. Yeah. Good. Other questions? Okay, so now there's a trick that people often glide over when going through the solution of this problem and present as a neat little bit of mathematics. So I'd like to talk about that neat little bit of mathematics, which is called a Bogoliubov transformation. This is how Bogoliubov originally solved this problem and obtained the dispersion relation. So this is quadratic, which is nice, but has spontaneous pair creation, which is bad, right? If you're looking for eigenstates, then it's not good to have a piece of your Hamiltonian that keeps spewing out extra particles, right? How can you be in an eigenstate if particles are always being created? So how do we deal with this? And the idea, which is due to Bogoliubov, is to, now I'm not writing it, not saying it the way Bogoliubov said it, but I don't think I'm saying anything that's really different from what he said. Think about what will actually happen if I time evolve the system using this Hamiltonian. So I started off with my sort of classical condensate. It's an estimate of what the ground state looks like, but it's not right. And because it's not right, it's not an eigenstate of the proper Hamiltonian. So when I start running the proper Hamiltonian on the sort of classical condensate, it starts popping out pairs of particles, because it doesn't have the number it wanted. But we do know that the full Hamiltonian has repulsion between the particles, so it won't keep doing that forever. At some point, we'll reach some new equilibrium where the quantum Hamiltonian has acted on our original guess and turned it into something that looks more like the actual ground state. And at that point, presumably, spontaneous production or annihilation of pairs of excitations will stop. So the idea is that this Hamiltonian transforms our classical guess at the ground state into something else. Let's call it psi. With a somewhat different and, if you like to think about entanglement, more entangled ground state. How do we find that ground state? Well, we make an inspired guess and we see if it works. Our conjecture is that the excitations above this new, better ground state are also bosons. That's not to be taken for granted. We know lots of cases in many-body physics where the excitations of the true ground state are not the same, don't have the same statistics as the things you made the system from. But we also know cases where it does work, right? So you take a Fermi gas whose excitations are fermions, you add interactions to it, the excitations are still fermions. So you might hope that if we take a Bose gas and add interactions to it, the excitations will still be bosons. And so Bogoliubov's idea is that rather than trying to construct this new state explicitly, which is difficult, we try to jump to the end of the process and work out what the dispersion relation of the bosonic excitations of this state must be. And there is a trick for doing that. But the important thing to get across, which I hope I have got across, is that what we are really doing is trying to describe the evolution from our classical guess at the superfluid state to the actual eigenstate of this somewhat quantum Hamiltonian. This still won't be exactly right either, right, because we dropped the higher order terms, but it'll be better than the classical state we started with. So we're trying to work out what the excitations above this modified condensate look like.
Yeah. I want to be more precise here. You said H hat transforms psi naught, but this H hat, are you referring to the truncated Hamiltonian here that you've written at quadratic order?
Yes, sorry. Yeah, so really I should have given that a different name. So let me instead say that what this shows is that the actual Hamiltonian can be approximated as an HQ for quadratic, and that HQ for quadratic is exactly equal to this. And it's this HQ.
Immediately before transforms. Yeah.
It's this HQ that transforms our classical guess into something else. The full Hamiltonian would also transform our classical guess into something else, but we have no chance of figuring out what. So we're looking at what the truncated version of the quantum Hamiltonian does. Yeah, Q stands for quadratic and quantum, but that's okay, because this is quadratic and quantum. Good. Any other questions? Experience shows this is the point where a lot of people feel that they sort of stopped picturing what was going on. I'm trying to get you through this while continuing to picture what's going on.
Do you have a concrete picture of what the A's and A daggers really do? I mean, they're not particle creation, like normal particle creation operators, right?
They kind of are. I mean, because the only Fourier mode where anything is different is k equals 0. Right? So because this condensate that I'm expanding around is completely uniform, the A's at k equals 0 don't really do anything because it's already full of condensate. But the A's at non-zero k do exactly what they used to do. They create a boson in that state. So you really can sort of picture them as creating bosons in the non-zero momentum states. The zero momentum state is now sort of occupied by the condensate and has to be treated separately. But the non-zero momentum states are just what they always were. They're plane waves moving about.
I'm still not exactly understanding the way in which this system is classical, because, for example, it seems like this argument would also imply that a weakly interacting Fermi gas is classical, which it isn't. Right?
Yeah, so the only thing that's classical is the state that I've started to expand around. And what I mean by classical in that context is that it doesn't have any entanglement. So I've started off, so when we refer to the classical state of a magnet, we mean a state where every spin is just described by some unit vector, nothing is entangled with anything else, and I use that as a starting point for describing what the quantum system really does, which is to entangle stuff with stuff. We're doing exactly the same here. In fact, there's a very close analogy between this problem and the problem of 2D, well, the problem of a ferromagnet. So an XY ferromagnet, right, where the moment can only lie in the plane, because a magnetic moment lying in the plane looks just like a complex number lying in the complex plane. And so there's a close analogy between what the local magnetization in a ferromagnet is doing and what the local phase of the coherent state is doing in a superfluid. And in just the same way that, for energetic reasons, all of the moments in a ferromagnet line up below some temperature, for energetic reasons, all of these complex phases in the superfluid line up below a certain temperature. Again, the exact direction picked is arbitrary and would be different if you did the experiment again. So, and that's what we do with ferromagnets as well, actually. Right? The actual ground state of a quantum ferromagnet is complicated. But we start off by saying, well, a good approximation to it is to put an independent quantum spin at each site and just give it a definite expectation value and then not entangle those with each other. And so that state is classical in the sense that it has no entanglement between the particles.
It's really just a product state.
Yeah, exactly. So we've taken effectively a product state of coherent states between the different momentum modes. But now we're saying, well, that's not really what the Hamiltonian would do. So let's start with that, but then try and generate the corrections to it by running the simplest quantum bit of the Hamiltonian on the classical state that we started with and seeing what happens. And the answer is it bubbles it a little bit, right? It generates some extra excitations, which is why we have these things. So we somehow have to try and get from our classical estimation of the ground state to the next step, which is the ground state of this truncated version of the quantum Hamiltonian, which is different.
So can I though repeat the first point of what Parasar said? What about the Fermi gas then, by these definitions?
Fermions are more complicated because for fermions you can never use a product state. Okay. Because you have to have antisymmetry.
Okay.
So there's kind of a deep difference there. The condensate, when you put every particle in the same mode, is automatically symmetric. So the condensate is somehow a state that would do as a state of classical particles and as a state of bosonic particles. Because the fact that everything's in the same mode means that it's already symmetrized. But it wouldn't do as a state of fermionic particles. So there's this sort of magic that bosons and classical particles connect at the condensate level, and the wave function we've written would do for either. Fermions and classical particles don't connect at any point and have to be treated differently.
Thank you.
Yeah, I have a question about this conjecture, because you say that the excitations above this psi are also bosons, but they come out of this quadratic Hamiltonian, right? And that only contains, if I'm correct, bosonic operators, so how could there be anything different? I don't see this.
So, yeah, I mean, that's a good question, right? You would... Yeah, okay. Let me take that as two questions. The first question, which is not the one you asked, but is, I think, an important one to answer first, is...
That's what a politician
If you're asking me, can I keep the triple lock on pensions? Sure. So a broader question is, how does it ever happen that we get simple excitations at low energies that don't have the same statistics as the excitations we had at higher energies? And what normally happens is some sort of reset process, right? So first you lose the excitations that you had at higher energies, and then some other ones emerge at lower energies. A great example is, you imagine I take a system of fermionic atoms and I condense it into a solid. So at high temperatures, the excitations were definitely fermions, and then they become completely stuck, they form the crystal. At that point, the particle statistics are sort of irrelevant, right? Because you're not carrying anything around anything else anyway. Everything's determined by energy, and it's doing what the classical particles would do. And then at lower energies, they remember that they're quantum mechanical, but now they're a bunch of oscillators, and the quanta of energy that go into oscillators are bosonic. So actually, whenever I take a liquid of fermionic atoms, make a crystal out of it, and then study its lattice vibrations, that system is showing transmutation of statistics. I made it out of fermions, but the low energy excitations are bosons. But your point here is, could that possibly happen? Because we've only got bosonic operators in our truncated quadratic Hamiltonian. How could we get fermionic statistics out of it? And that's kind of right. But it's surprising how... So if, for example, I had additional fields in the Hamiltonian, I can have gauge fields interacting with bosons and get fermions out at low energies. But I agree with you, actually. You're kind of right that I can't really expect anything other than bosons here. But what might have been the case is that there are no single particle excitations for the state that results at all. I mean, in some sense, I'm not... When I say imagine the excitations of bosons, extra stuff comes with that, which is assuming that they can be counted and that I can say this boson is over here, this boson is over here. So I'm imagining that my low energy excitations are still in the form of kind of a dilute number of basically independent particles. That might not have been true. So, and then I can't even talk about statistics, right? If I can't isolate a bit of an excitation over here and a bit of an excitation over here and wrap them round each other, then I can't even define what their statistics are. So I think there are like strongly correlated options that just wouldn't yield to this treatment at all. So in some sense, what we're really saying is not just assume that the excitations are bosons, but assume that they're not confined, they're sort of asymptotically independent bosons that can be counted and separated in the way that usual particles can be counted and separated. That was either of those questions the question you asked?
Yeah.
Good. Well, that's something. Okay, so same question again. Do we have a picture of what we're about? Okay. So now let me show you Bogoliubov's trick for jumping to a description of these excitations. It's totally insane.
How does he compare to Landau in comprehensibility?
It's not that insane. I mean, Bogoliubov gives us a calculation. It's just the calculation is insane. That's a step better than Landau sometimes, right? Where you actually look at it and you think, I'm not sure this is a calculation. I think this is just an argument. So suppose that the creation operators for the true bosonic excitations, let's give them some names, BK dagger, are linear functions of those for the original ones. And this is sort of related to that supposition that the bosonic excitations of the new ground state will somehow be similar in nature, countable, separable to the ones that we had before. But now we can't just say that annihilation of an original boson will be annihilation of a new boson, because that means that if the Hamiltonian spontaneously creates the original bosons, it will also spontaneously create the new bosons. So it must be, if this idea works at all, that the operator that annihilates one of the true excitations is a combination of the operator that annihilates an original excitation and one that creates an original excitation.
Sorry, I'm getting lost with the true and original excitations. What is what here?
So, original is the stuff that we had in the gas in the beginning. Right? So we made this thing out of bosons, and the AK daggers create those bosons. Those are also the excitations above the classical approximation to the ground state, because the classical approximation to the ground state just makes a condensate in the k equals 0 mode, and everything else behaves the way it did before. So, AK dagger just literally creates a boson moving with momentum h bar k, an original boson. But then what we note is that once we put quantum fluctuations back in, even in this approximate way, the number of original bosons is no longer conserved. So I can't say that my ground state of the quantum problem is the same condensate that I was using for for my first approximation, because if I run the Hamiltonian on that condensate, it starts spewing out extra particles. So now what I'm trying to do is to ask what then is the ground state of this Hamiltonian, the one with some of the quantum corrections. And that's difficult because I would have to run this Hamiltonian for a long time, wait for the extra particles to equilibrate with the stuff that was already there, and that's just not easy to do. But Bogoliubov says, let's try to just jump ahead and work out a theory for what the excitations of that true ground state. So by true, I mean the ground state of this HQ.
I got it now.
Okay, good.
What's original again? Yeah.
Yeah, so I guess true is in quotation marks, because even this is not the exact ground state of the Hamiltonian we started with, it's just a better guess.
Excitations of HQ.
Yes, excitations of HQ.
So in some sense, can I think of it as like HQ? Okay, so I started from my coherent state. Now I'm looking at the fluctuations. Now I have this HQ Hamiltonian describing like the low energy fluctuations. But this I can now see from the coherent state that I'm spontaneously creating these pairs of particles. And so now by the Bogoliubov transformation is something like I need to look at how these particles that are created by the A's are now going to further condense again into...
Exactly. And they will add to the sort of classical condensate we had to begin with, and then we'll get some excitations above that, which is what we really want to describe. It's a bit like, I don't know if this analogy will help, but it's a bit like thermal expansion. So if I say that my solid is a set of harmonic oscillators, then as I heat it, it doesn't expand. Right? The equilibrium position of the oscillator stays exactly the same, it's just the excitations around it get wilder. Thermal expansion comes from the fact that the potential is asymmetric that the atoms are sitting in, and so as I heat it and create phonons, they also change the equilibrium position of the oscillator, and that makes the solid expand. This is a bit like that. The excitations that we're creating are changing the sort of equilibrium state around which they're being created. So once we let it create some of these A daggers, that actually also changes the condensate around which they're being excited. And we want to kind of take that out of the description to talk only about excitations above the new condensate.
But instead of temperature, it's quantum fluctuations.
Yeah, exactly. Details. Yeah, please.
Is the minus k just a choice, or what's?
The minus k is an inspired choice. So you could make this general, right? You could just say it's some sum over q combinations, and you could boil it all through, and you would eventually find this is what it has to be. But the argument is, so what we're going to do with these is to substitute them into this Hamiltonian and see if there's a choice of these parameters that eliminates the spontaneous creation terms. So the argument is that if we look at this with respect to a new ground state, so we use the B operators instead of the A's, our conjecture is that there is some ground state around which those B dagger terms wouldn't arise. So we're going to try and substitute this into there and pick the UKs and VKs in such a way that the B dagger terms go away, and then we will know that we're describing the excitations around the correct ground state because we're no longer seeing spontaneous particle creation.
And pairs of A.
And you can see from the form of it that if something's going to cancel off, what we're basically saying is we want to turn this term into this term, which involves turning A of minus k into A dagger of k. So those are the things that are better mix.
Well, I mean, it's also inspired in the sense that now B really creates something that has momentum k, right? I mean, preserves momentum in that sense.
Yeah, okay, you can also argue it just from translational invariance. Oh, yeah, right, which is yeah, I agree. Yeah, you're expecting your excitations to be labelled by a definite momentum. So if I'm annihilating something with momentum k, that had better be the same as creating something with momentum minus k, or I've screwed up my momentum accounting. Good. Any other questions? Okay, so the idea, which we are not going to do in detail, is to sub this into the Hamiltonian HQ and choose UK and VK so that there are no B dagger K, B dagger minus K terms. And of course, if there's no way of doing that, then Bogoliubov's conjecture is wrong, and we don't know how to attack this problem. But it turns out that there is a way of doing that, and so you can just substitute. Well, you have to invert this to get A and A dagger in terms of B and B dagger, substitute them in, and you just find that there is a particular choice of the UKs and VKs for which the double creation terms can be removed. And so what we end up with after that transformation is another correction to the constant part of the energy. Right? So this E0 tilde is not the same as that E0, and that reflects the fact that this extra bit in the ground state has changed the energy. But then we end up with just a sum over K, EK, BK dagger, BK, because we chose our U's and V's to eliminate the rest. And so this now can be interpreted as independent bosonic excitations above the new estimation of what the condensate looks like with this dispersion relation, and putting in the exact expressions for the UKs and VKs, we get the following interesting form for the dispersion relation, which is the square root of the original one times the square root of the original one plus 2g times the condensate density. So the remarkable feature of this problem is that we can actually write down, within this quadratic approximation for the fluctuations, the new dispersion relation for excitations once we put the quantum fluctuations in. And this is what we get. How does this behave? Well, it's obviously got a linear in K term in front of it all the time. But then what this term does depends on how big K is. When K is small, this is a constant, and we just get linear excitations with a certain sound speed. When K is large, we can neglect this interaction part, and we go back to just the free boson dispersion relation. So what we conclude from this analysis is that the excitations above our sort of quantum dressed ground state for the problem are still rotationally isotropic, so the energy depends only on mod K, but now where we previously had just a quadratic dispersion, we now have linear at low momentum and then rolling over to quadratic as we go higher up. And we can work out the length scale or the momentum scale at which that rollover happens. It's just, of course, the scale at which this term is equal to this term. And so we can define a K0, which is where we go over from these linear excitations to these quadratic ones. And just by comparing those terms, it's 1 over h bar, the square root of 4mg times the condensate density. So maybe unsurprisingly, as the condensate gets denser and denser, this crossover moves further out. But it's always the case that sufficiently high energy excitations just have the same dispersion as the original bosons, but the low energy excitations are now different. And the way to think of these is a sound. It's a sort of sound. If you like your theoretical terms, this is a Goldstone mode. So the superfluid, when it formed, spontaneously broke this phase symmetry. If you spontaneously break a continuous symmetry, then you have to have some gapless excitations that restore that symmetry. So what this is, you know, all of the phases in different bits of the superfluid are lined up, but they can wiggle. And this excitation that's linear is just those phases wiggling back and forth. And that's a bit like a sound wave. The reason it has to be gapless is that if I make it infinite wavelength, then it corresponds to all of the arrows turning together. And we know that's just moving me from one ground state to another, so it can't cost any energy. So we can see on sort of general theoretical principles that if we spontaneously break this rotational symmetry of the phase of the coherent state, we ought to have a gapless mode, but it's nice that this Bogoliubov calculation produces it exactly and shows that it's linear.
So under what approximations were involved in saying that we broke the symmetry by adopting the phase? I mean, is that something, you know, because what we've done, you had the proper Hamiltonian and now you've got the HQ.
Yeah.
Is the statement that we broke the symmetry an exact statement based on analysis of the proper Hamiltonian?
In the discussion I've given here, no. We chose a coherent state approximation which has the property that it's capable of breaking that symmetry. But if you look at, you know, you can do numerics on the actual Hamiltonian, you know, quantum Monte Carlo, this kind of thing. And what happens when you do that? So the numerics can never spontaneously break the symmetry. But what they give you is a superposition of, you know, a condensate with a definite phase all across it where the phase is 0, and a condensate with a definite phase all across it where the phase is π/2 and so on. And they give you a so-called cat state of all of these different condensates with their different phases, which is exactly the same statement that if you quantum mechanically solve a model of a ferromagnet, it will not give you a state where all the spins are lined up in a particular direction. It will give you a superposition of all spins up with all spins down and any other things in between that are orthogonal. So, in a sense, it's a question of meaning. Right? What we mean by saying that a system shows spontaneous symmetry breaking is that it, at least for a finite-sized system, its true quantum ground state is a cat state of these different classically ordered states. But the argument is that the time that it will take the system to find that true ground state is unobservably long. So what you actually see when you do this in the laboratory is that some bit of stray field causes it to pick one. And then, you know, in the end, it would find the others, but that would take a huge amount of time.
So that probably then answers the second question, which is that, so this linear dispersion, which has come out of HQ, is still predicted to come out from attempts to go beyond quadratic order.
Yes. Yeah, I mean, if I thought the picture changed qualitatively according to our best evidence when we added more fluctuations, then I wouldn't be telling you about this. But it seems like actually this expansion procedure, even though it's not formally mathematically controlled, is basically fine. But again, we only really ever know that by comparison to numerics or experiment. But yeah, I mean, you can measure the dispersion relations of weakly interacting cold atom gases of bosons, and they look like this.
Are we going to talk about rotons? And
We are.
good.
Possibly even today.
Okay, if I'm quiet.
I don't mean to make anybody quiet. Right? I think the whole point is let's think about what we're doing. Yeah.
How do we come to the conclusion that these excitations are related to the changing of the phase of the order parameter. Because with like magnons and stuff, you're always like changing the spins, so it's kind of like a obvious kind of description of them. But here, I find it more tricky to.
Yeah, I think that's a fair point. The argument for why they should be, which is not perhaps quite the same as showing you how to see in the calculation that they are, is that the classical analysis we did to start with, where we just said let's use a single coherent state and see what the Hamiltonian would like, told us that it doesn't care what the phase is, but it really cares what the amplitude is. So at the classical level, this Hamiltonian pins the amplitude at mu over g, but it doesn't care at all what the phase is. So classically, this phase degree of freedom is completely soft. Quantum mechanically, of course, different bits of the system start talking to each other and it becomes rigid. And evidence for that rigidity is that we now have a finite energy cost for rotating the phase in different places of the sample differentially. And that's what these modes are. So a plausibility argument is that the only thing that looks like it could be low energy based on the classical theory is some rotation of the condensate phase. Yeah. The classical theory already told you I have a definite answer for what the amplitude should be, and it's mu over g. So your sort of soft degree of freedom before you do any of this is the phase. We can do a little bit better, and we'll do a Landau-Ginzburg theory where the phase appears explicitly, but that has to be kind of coarse-grained. I don't know of a very easy way to see in this language that is what's happening. Other questions? Okay, so let's, as what will surely be our last board of the morning, then come back to the question that we started with, which is, does this help us with our question about superfluidity? And the argument is, yes, it does. Because what did the Landau argument need? It needed the dispersion relation of the non-condensed excitations of the system, and we've just calculated the dispersion relation of the non-condensed excitations of the system and shown that unlike in the case of the BEC, where the spectrum was quadratic, the spectrum of excitations in this interacting Bose gas is linear, at least at low energies. So that's crucial, because if we now revisit the Landau argument, we can see that there's a huge difference between something with a quadratic spectrum, like a BEC, and something with a linear spectrum, like a weakly interacting Bose gas. So let's recall how the argument worked. We put the condensate into motion in the lab frame with respect to some stationary pipe or other set of obstacles. And so it flows along with a velocity v. And Landau's argument was that in the co-moving frame, that is to say the frame that's moving along with the fluid, that looks like the walls moving backwards at minus v. In other words, it's a time-dependent perturbation to a stationary condensate. And the question is, does that time-independent perturbation destabilize the condensate? And so the argument was yes, because in the lab frame, the excitations out of the condensate were quadratic in momentum. In the co-moving frame, you shear this to get the expression for the energy in that frame. Shearing something quadratic will always make some negative energy states.
What do you mean by shearing?
I literally take the picture and do, no, yeah, because the relationship is that the energy in the co-moving frame is the energy in the lab frame minus V dot P. So if I look along the direction of motion, this transformation is just literally shearing the plane on which I've drawn the graph. So that will, because this is quadratic and shearing is linear, that will always pull out some set of negative energy excitations here. And the argument then is if the walls are sufficiently complicated, there will always be a matrix element for those to be created. And because they're bosons, they'll be created without limit, and this will destabilize the superflow. But now, obviously, if I do the same analysis for a weakly interacting Bose gas, where we've just shown that the low energy part of the spectrum is linear, so down here, E is approximately equal to some speed of sound in the fluid times K. This is lab frame. So now you can see this is robust to a certain amount of shearing. And the co-moving frame, we reduce the velocity of these excitations. Sorry, keep writing K when I don't mean it. We reduce the velocity of excitations that are going in the flow direction of the fluid, but we don't reduce it to zero. And so there aren't any negative energy excitations until we exceed a certain critical flow velocity. So this argument, so the Landau argument predicts stable superflow until the velocity of the flow becomes greater than the sound speed that came out of this Bogoliubov treatment. So in other words, it predicts, if we take it seriously, superflow with a finite critical velocity. Now, there are two loopholes to this argument. One is that this is not the complete set of excitations that you can create in a superfluid. So there are other things that can happen in superfluids beyond the excitation of little sound waves in the phase field. And one obvious one is vortices. And so in reality, the way superfluidity tends to be destabilized is that vortices get shed from the walls, not that sound waves get shed from the walls. We will talk, although on Friday, about how to describe those vortices, but typically what we find is that actually the real critical velocity of superfluids is much less than this estimate, and that's usually because vortex-mediated instabilities kick in at lower flows than sound-mediated instabilities. So this doesn't prove, actually, that the state we've written down is a superfluid, but at least it proves that it's not destabilized by the emission of sound waves from the walls in the way that the BEC would have been. Actually, in the BEC, it's not really sound, it's just particles. It is only sound now because we have some interactions. The other issue, which Andy alluded to, is that this is a theory for a weakly interacting Bose gas. And the case that we normally look at in experiment, or that we discussed in the phenomenology, is helium-4, and helium-4 is not weakly interacting. So if you actually measure the dispersion relation of excitations out of the ground state of helium-4 in its superfluid phase, you do indeed get a linear dispersion at small momentum, and you do indeed recover a quadratic dispersion at large momentum, but something happens which is not at all in Bogoliubov's picture of the world in between. And so this thing is referred to as the Roton minimum in the dispersion relation. It is not present in the theory of the weakly interacting Bose gas. It is not present in experiments on weakly interacting Bose gases either. It develops as you increase the strength of the repulsion between the particles. Right? Helium-4 has quite strong contact repulsion at the densities where the experiments are done, and so the Roton minimum is quite well formed. Different people tell different physical stories about what the nature of these excitations is. Feynman, I don't know whether he coined the term Roton, but he definitely popularized it. His picture was that this is kind of a quantized version of a smoke ring propagating through the fluid. So it's got some kind of circulation about it, whereas a sound wave just kind of waves from side to side. Philippe Nozière always took the view that actually this is incipient solidification. This has a certain length scale attached to it, and his picture was this is going to turn into a Bragg spot if you turn up the repulsion much higher, and it's associated with the fact that if I pressurize the helium, it will solidify. Obviously, solid helium is going to have to develop a phonon, and it's going to develop it at a K that corresponds to the lattice spacing. So I don't want to say too much about I don't know what the true physical interpretation of the Roton minimum is, which is why I don't want to say too much about it. But I guess it's important to point out that in the examples we've been studying, actually the things that would destabilize the superflow in the Landau argument when we shear the dispersion are these things, right? So it's not shedding sound waves, it's shedding rotons, whatever they are. Yeah, Parasol.
Is there any analogy to like classical fluid? Do we see something like this in classical fluids, where you get certain higher energy excitations beyond sound waves?
In the same dispersion branch? It's a good question. I don't remember seeing such a plot, but I don't know that the answer's no. If Nozière's picture is right, then of course it should be, right? Because you'd think that phonon development is pretty classical. So you'd think that if you pressurized any fluid close to the point where it's solidified, it would have to make something that looked a bit like this. So I suspect the answer is yes, but I haven't actually seen this plot out to the relevant Ks for a regular fluid, so I don't know the answer. I'll see if I can find that out. Good. So yeah, just to emphasize, the Landau argument obviously also predicts a finite critical velocity even in this case, but now the critical velocity is given by the slope of this line, not this line. So the weakly interacting Bose gas will only, if we ignore vortices, will only go normal when the flow speed exceeds the sound speed. The strongly interacting Bose gas, which is helium-4, even if we only think about these things and ignore vortices, will go normal at a slower speed than that, because it's when this Roton minimum touches down that you'll start producing instabilities.
So I'm sure you defined this, and I've just forgotten it, but when you set up the Hamiltonian for the weakly interacting with G, what definition did you give for the scale against which G is small?
You mean what makes it weakly interacting? Yeah. Well, in a sense, I didn't really.
Okay, I didn't forget it.
And actually it turns out, as you can see from the solution, that it becomes a length scale question. This treatment I've given, sort of all that really changes, at least at the quadratic approximation level, as you change G, is that this crossover between sound wave-like excitations and free particle-like excitations moves out to higher momentum.
Yeah, but then as you crank up G, you don't get to a Roton.
No, that's right, but of course the truncation to the quadratic Hamiltonian is going to become worse as G gets stronger. So
Okay, so in the quantum simulation solutions, do you find the roton?
can you get a roton? From memory, the answer is yes. I think when they say that the roton appears at stronger repulsion, I think there's numerical support for that statement. But it wouldn't appear in this analysis because we truncated the Rotonian, and yeah, the roton is some sort of non-linear thing, which I guess is why Feynman got to thinking about smoke rings, because they're clearly non-linear.
Well, and also, the rotons are certainly there in the XY model, right? I mean, there's vortices in the XY model.
So there certainly are vortices. But whether I should... It's not obvious to me that what I should say about that minimum in the dispersion relation that's continuously connected to sound is that they are vortices. There certainly are vortices, and they are actually present even in the weakly interacting Bose gas, as we'll see on Friday. I think saying that the roton is those vortices is a more complicated statement that I don't think I want to commit to. I think it's a third thing.
So the thing that breaks down, it's okay. I'll phrase it differently. Do you still expect that the linear regime is valid even in a strongly interacting system, just with this smaller cutoff, or do you? It could also be that the actual excitations then are, I don't know, some bound together bosons, like molecules or whatever.
Yeah, agreed. So here we've deliberately made the interactions repulsive, and that avoids the question of bound state formation.
Not necessarily, right? I mean, electrons are also repulsive, and yet.
Oh yeah, but that's in the presence of a Fermi surface, right? So I think I think for bosons it's easier to say that we're never expecting purely repulsive interaction to lead to bound states, because you don't have Friedel oscillations or any of that stuff. So there's no sort of mechanism in the ground state to change the sign of the interaction. So I think we're safe saying that if the bosons are repulsive, we should never have to worry about bound states. We could worry that at a finite strength of the repulsion, the condensate density would vanish. That doesn't happen in this analysis, but for fixed chemical potential, the condensate certainly gets weaker as you strengthen the repulsion. You might worry that fluctuation effects would make it go extinct at some finite value of the repulsion. And then, of course, all bets are off. But I think that's the way to look at it. If we form a condensate, which is spontaneously breaking the U1 symmetry, then we have to have a Goldstone mode. There's only one generator of U1, so it has to be linear. So that's the way I'd look at it. It should be robust as long as the superfluid state itself is robust, but there's nothing that guarantees that beyond a certain strength of repulsion, you'll never even form a superfluid, and then we can't say anything about what the excitation should be.
You may have just answered this question, but you said that if we were to consider keep higher order perturbations, higher order corrections to the fluctuation that we add to our classical system, classical state, that we still get this picture. So then how would we get this sort of roton? How would we end up including this roton in the dispersion relation? Is it like a non-perturbative effect? Would we need to?
That is a very good question. I don't know the answer. I mean, if it doesn't appear in any order of the further expansion, then surely it is a non-perturbative effect. But I'm not completely sure that it doesn't. I know that the sort of stuff near k=0 doesn't get materially affected, but changing the sort of monotonic nature of the dispersion well away from k=0, I'm actually not sure whether that would come out of a finite number of those correction terms or not. And of course the numerics don't help, because they just tell you that if you put everything in, it's there. Yeah. No, good question. I don't know the answer.
but you can't do, you must be able to do numerics based on, ramping up the level of non-approximation.
Ah, so you mean
You guys don't care.
do numerics, including increasingly higher orders, and see where it appears? I mean, that might have been done. I don't know all of the literature on this. It would be a natural thing to try and do. I guess maybe part of the issue is that the earlier stage of the Roton literature happened at a time when those wouldn't have been easy to do. So people might have regarded these questions as dead and buried before it would have been easy to bug it on a computer and see what happened. But I agree, it would be a very natural thing to try. I will try and find these things out. Other questions?
Sorry, when you look at this dispersion with the BKs, if we were to substitute back in this in terms of the AKs, it sort of gives us a picture of how we can think of a sound wave in terms of creating and annihilating our original bosonic modes. Is that an okay way of interpreting it?
It's okay, but you have to remember that you're doing it against a reservoir of a finite density of those original bosons.
Yeah.
So the ground state of HQ doesn't have any of the B's, but it does have some of the A's. But yes, so with that footnote, yes, that's right. So what it's telling you is that the particular combinations that we had to choose to make this Hamiltonian into this form are telling you the sort of combination of original whole and particle content that the sound waves have. And we'll see something very analogous happens in superconductors. So when I make an excitation of a superconductor, it's partly electron and partly hole. And it goes along very similar lines to this. Good. Any more for any more? Mark?
Just to sort of connect things back to things that were done last week, with this, so what should I interpret as being the density of like the normal fluid and superfluid from that conversation? Because we have the original, because we have this sort of unperturbed condensate, but now we've added this sort of extra condensate of pairs of bosons coming out of the...
Yes. So I think you should interpret this thing, so everything that's giving rise to this energy as the condensed fraction, including the bits of the condensate that, it's not so obvious. In this weakly interacting picture, it's really hard to say, actually. I think in some sense in this weakly interacting picture, it is still the case that everything is in the condensate, at least at zero temperature, right? Because at zero temperature, I'm not going to have any of these bosons because the dispersion's positive. So at zero temperature, everything is now in the quantum dressed condensate. It's tempting to say that the original condensate, the classical one that we had, is the condensate part. The extra A's that we generated in getting to the new ground state are the non-condensed part that's still taking part in the superfluid. And that's why the superfluid fraction is always 1 at zero temperature, even though the condensate density isn't. I think that's kind of right, actually. That and you can see it here that these extra A bosons have been incorporated into the superfluid condensate, so they'll participate in the superflow. But in terms of the original A's, they're not in the K equals 0 state. So we've sort of extended the condensate so that it's K equals 0 in term, well, not K, it's no longer just living at K equals 0 in terms of the original A bosons, but it is still functioning as a single coherent superfluid. I think that's the right thing to say.
Maybe one short one. The wave function, the quantum dressed wave function, can you say something about the entanglement? Is there anything interesting?
I think there probably isn't anything very interesting at the HQ level because it addresses all the K's separately. So the most it can do is entangle K with minus K, and it can't do anything beyond that. So there'll be some sort of pairwise entanglement between the mode at momentum k and the mode at momentum minus k, but it's still a product state of all those different pairs.
So is that to be thought of as a fractionalized condensate then, after you've turned on these fluctuations?
You mean in the sense that, no, I don't think so, because there's still only one state that has macroscopic occupation. So normally what people mean by fractionalized condensates is there's more than one mode which has occupation of order n.
Yeah.
It's still the case here that the only mode that has occupation of order n is the k equals 0 mode. It's just it's acquired a bit of a quantum tail if you look at the distribution in terms of the original k's. But that's made of a lot of modes, each of which is only slightly occupied. So there's still no ambiguity about where the condensate is centered. It's centered at k equals 0. Okay, we should probably get lunch. Thank you everyone for your questions as ever.
If you had like a finite number of k modes, then you've lost the part